Okay, so let's just start out with some of the basics. So I think when you first start learning about emissions trading, pricing, and cap and trade schemes, we think about abatement and marginal abatement costs. And so we learn that at the optimal emissions price, if our marginal benefits of abatement look like this, a downward sloping curve, and the marginal costs of abatement are upward sloping, then the optimal emissions price is where the marginal benefits equal the marginal costs. It gives you the optimal price and quantity. And you can, of course, implement this. If you don't have any uncertainty or any other worries going on, you can implement this either by setting your price at the optimal tax, or setting a cap and trade system, a quantity system, at your optimal quantity of emissions implied by that abatement amount. And more importantly, if you have a bunch of actors, either of these mechanisms will equalize abatement costs, marginal abatement costs, across them. And then, okay, so then you have a pot of revenue. Okay, you have the emissions price times the remaining emissions. So what do you do with that? Well, if you allocate that just lump sum, either you can say grandfathering the permits based on some historical emissions factor, then it doesn't affect this equilibrium. If the allocation is unconditional, it's just you get this pot of money regardless of what you do, or you get this number of allowances regardless of what your subsequent behavior is. So when we start thinking about output-based allocation, though, where we're thinking about an allocation program that does affect marginal behavior, and then we can't really look at that marginal abatement cost, marginal benefits intersection anymore, because we have to think about what's going on with output, what's going on in output markets, product markets. So it's a little bit of a different perspective on abatement. So to give you an idea of how this works, so let's just start with a simple partial equilibrium model. So that means we're just sort of looking at a representative firm in the sector. We're not thinking about what happens in the rest of the economy. Just for starters, let's assume that marginal production costs are constant, but they are a function of how emissions intensive you are. So if your emissions rate here is mu, as you try to decrease your emissions rate, that's going to increase your constant marginal production costs. So C is going to be a function of mu. So in this case, total emissions are going to be your emissions rate times output, and you're facing an emissions price of T. You face a demand for this product, inverse demand so the price is going to be a function of the total quantity produced in the sector. So in the equilibrium, what this representative firm wants to supply has to equal what's demanded at that price. And we can also think about a lump sum allocation of rents that may be R. Okay, so first let's just redo what presumably you've already done, thinking about incentives with grandfathering. So here's the profit function of the firm. You have revenues minus production costs minus tax costs plus whatever rents they're getting in their lump sum allocation. So what does this firm want to do with this problem? Okay, so you're maximizing both with emissions, with respect to emissions intensity and to how much you want to produce. So maximizing with respect to emissions intensity, well, it's going to raise your cost, so that's basically your marginal abatement cost. And you set that equal to the emissions price. Okay, so you get marginal abatement cost equals marginal price. With output then, this representative producer will want to produce as long as until the cost inclusive of the marginal tax cost. So here you have an additional unit of production. You're going to have to pay more emissions taxes, tau T times mu, the marginal emissions, okay? So these are your inclusive costs equals the price. So we have, in a simple model, we just have constant marginal cost. So then in equilibrium, it must be, it's basically then the demand side that determines how much the quantity is. So at that cost, the quantity demanded is Q, and that must hold in equilibrium. Now we see R doesn't show up in this first order condition. It's just a transfer. And so what this happens here, and so in this model with the constant marginal costs, in the normal part you have zero, you would have zero profits from selling the good because the price just offsets your costs. And the transfer is like a windfall profit.
So what was R again?
Yeah. R is the lump sum allocation of rents, I guess R for rents. So it's if you have just an allocation of emissions allowances that's not conditional on anything you're doing, the value of that allocation is R. So that just, it shows up in your profit function, but not in your first order conditions because it's fixed. It doesn't change based on how much you produce or how much you reduce your emissions. How's that determined? Okay, so if you haven't had any examples yet. So in the US, in the sulfur dioxide trading program that was set up under the Clean Air Act amendments, they specifically used grandfathering. So they did an exercise and calculated for the plants that were going to be covered by the program, what were their emissions in prior years, so prior to starting this program. So these were emissions that were already set in stone and they couldn't influence it. So, but they used that as a proxy to calculate, so what would sort of the needs of these firms be in terms of what kinds of emissions they would have in the future and emissions allowances. And so they were grandfathered into the program. So they used this calculation and they said, okay, well you used to emit 100 tons, so we'll give you 80. So it was often in proportion to that. Then also in the first phase of the EU ETS, they used this for a lot of firms, including the electricity sector. And then what they've found out is, so you see what happens in this equation here. This is a competitive representative firm. So they're not setting the prices, but any increase in their cost in equilibrium just gets fully passed on to the consumers. Because price has to equal marginal cost in equilibrium. So if you're raising the marginal cost, it raises the price that the consumers pay. And so these guys always have zero profits from production. So so they don't lose money by having to pay more of the emissions tax. So what happens by giving them the grandfathered allocation, it actually gives them positive profits. So this is a very simple model. In reality, you may have heterogeneous costs, you may have producer surplus and like an upward sloping supply curve, and then you will have some effects of emissions pricing on profits. But so it's a big. If you think it's important to compensate any losses in profits, then it's important to know how much. And so the notion that a fair allocation is basically what, close to what you need in terms of the emissions allowances that you'll have to surrender to be in compliance is almost always a vast overstatement of what kind of allocation will keep would keep a company whole in terms of their profits. And this lesson was learned very quickly in the first phase of the EU ETS, where they did not listen to the economists saying that the electricity sector in particular doesn't have to compete internationally, is very good at passing on costs to consumers. And they saw, large windfall profits in that sector. And they had their allocations ramped down a lot in subsequent phases. So grandfathering is really considered, I think, it's a type of compensation mechanism. So let's think a little bit more in this model before we get to the output-based rebating of what's going on with abatement. Before we just had a marginal, upward sloping marginal abatement cost curve. In this setting, when you're thinking about production and emissions intensity, you have two options now for reducing your emissions. So one is reducing your emissions intensity, but the other is also conservation. So you can produce less, and that reduces your emissions. And these are both, valid ways of reducing emissions. So what is output-based rebating? So this is used in conjunction with emissions pricing, and it's where you take some or all of the revenues and you allocate that back to the affected firms, but now it's going to be conditional on their behavior. So you allocate it back in proportion to their output. So the more you produce, the more you get. So this is usually implemented using like an emissions intensity benchmark. So we think on average, firms in this sector would have the given emissions intensity, and we allocate back that way. That's one way of keeping it fairly revenue neutral. In the latest EU ETS phase, it's a benchmark, more of like among the top performers in the industry. So it's less than 100% of the average emissions. So it's not quite revenue neutral within itself. The important thing to remember, though, is that when you allocate based on output, it fairly functions like a production subsidy, because the more you produce, the more allocation you get, so the more money you get, the more subsidy you get, rebate. You can call it all of these things, but politicians will prefer certain things over others. Refunding or allocation sounds nicer. Okay, so there are actually several ways that you can implement output-based rebating, and it kind of just depends on what your emissions pricing instrument is going to be. So one example of doing it, setting it up in a naturally revenue neutral way, is by using tradable performance standard. So this is where the policy sets the average emissions target, your emissions intensity target, and then you use tradable credits to achieve that. So in this case, firms that are more emissions intensive are going to have to buy credits, going to have to pay for those extra emissions, and those that are less emissions intensive than the average, they're going to get excess allocation that they can sell. But everybody's getting the same average allocation, so everybody's getting the same subsidy, in a sense, output subsidy, but you're going to have different net emissions payments. But everyone has the same emissions price and the same subsidy. So this was used in the US to phase out lead in gasoline. They used a tradable performance standard program. I also think it's akin to fuel economy standards, where manufacturers have a fleet-wide emissions. Well, in Europe, it's an emissions intensity. In the US, it's a fuel economy standard, and they can average across all their vehicles to meet it. Okay, so output-based refunding. So this is refunding. Tax refunds sound like a good thing. So this is the mechanism that Sweden chose to implement the NOx tax, where the tax, so you have a tax on emissions, and then the revenues are taken and they're refunded back to participants in proportion to, how much, in terms of how much their power production, basically, so their share of total power production. And then we have output-based allocation of emissions allowances. So this is where, you have to buy or surrender allowances for all of your emissions, but you get an allocation in proportion to how much you produce. Tons of steel or however you want to measure that. So this was probably the most explicit proposal for this kind of allocation was in the Waxman-Markey bill in the US, the American Clean Energy and Security Act, which passed the House but didn't pass the Senate, and so it's law. It never became history. But also a form of this is, being used in the EU now with the benchmarking program. And Australia pretty explicitly chose a form of output-based allocation until the new prime minister decided to get rid of the carbon tax that was going to phase into carbon trading. But anyway, so you can see the popularity here. So the idea of wanting to keep the revenues in the system and not overburden the firms as if they just had to only pay the tax, and help them out. So how does this work, though? Okay, from the firm's perspective, so we have the same firm, but now instead of a lump sum allocation, we have a per unit allocation of rents, so which is like a subsidy, so we'll call it S. And so now the profit function looks like this. So we have profits being revenues minus production costs minus net tax payments. So now you still have to pay the same price on your emissions, T times your emissions rate, but now you get a subsidy per unit that you produce. So it actually sort of turns into this, you will have a net tax then if the value of your emissions intensity is greater than the subsidy, you get a net payment if it's less. So we just have this nice simple representative firm. So if we assume that the scheme overall is revenue neutral, or they're all identical and they're going to have the same emissions rate, then in equilibrium, this is going to wash out. So we still have for the intensity, the first order condition with respect to the emissions intensity, you still have the same equation as before. So you're equating the marginal cost of reducing your emissions intensity with the price of emissions. Okay, so that part isn't distorted if you have the same T. But here on the production side, though, it's now the subsidy, the allocation, shows up in the first order condition. Okay, so it's going to be affecting production decisions. So we have now the same maximizing with respect to Q. We have the same marginal cost of production, same embodied emissions tax, but now you have this output subsidy. And again, this is a competitive firm. This is going to get passed back to the consumers, and so what you get is in equilibrium. So these costs are lower. Given the same emissions price, these costs are lower, so you get more output. Okay. This is just to show you, you don't have to set it up in the way that I did with the emissions intensity mu. You can set it up more using, so your cost can be a function of both your output and abatement, and your emissions are then a function of your output and your abatement efforts. But you end up with effectively the same thing. So you have maximizing with respect to abatement, you get these cross partials that you can think of as the marginal cost of reducing your emissions intensity, equaling the emissions tax, and here you have marginal production costs and marginal emissions. Okay, so it's based on the same setup, but I find it's for me it's a little simpler and more intuitive to think of this, because you can break out your focus on improving your emissions intensity very clearly versus conservation as a means of reducing emissions. Okay, so does output-based rebating compensate firms in the same way as grandfathering? So what do you think in this model? What does it do to firm profits? Okay, so remember our equilibrium condition here. So in equilibrium, the price is going to equal the marginal cost plus whatever the net tax is. So what happens to profits?
Nothing really.
Nothing, exactly. It gets passed on to consumers. So this is a perfectly competitive firm with a very simple, we have constant marginal costs in this case. So the price is always going to equal whatever the fully loaded constant marginal costs are. There are never profits. Everything just gets passed on to the consumer. The only time we saw profits was when we actually transferred them to the firm and gave them a windfall. So in this sense, the subsidy here doesn't necessarily compensate firms, because the firms, regardless, get compensated because the price. So if their costs go up, the price goes up and offsets that. Okay, so now, what else is happening here? So if we set the benchmark to be, to make the program revenue neutral, so that's equal to the average equilibrium emissions, then we do have, though, it's not that costs don't go up at all, that we're offsetting the tax costs, the embodied tax costs in the product. Okay, so those costs don't go up, but the production costs are going to go up because, to meet the emissions target, they have to become less emissions intensive. So that does raise production costs. So prices will go up somewhat. It's just you're not asking consumers to also pay for the embodied emissions remaining in the product. Okay, so if we want to think about our different forms of rebating, okay, suppose we have an emissions tax with 100% output-based rebating. So the bar indicates which variable is fixed. So in this case, our tax is fixed. So, and the equilibrium subsidy is going to be the tax price times the equilibrium emissions intensity, and that's going to be determined, by the tax. And then you have output prices in equilibrium. The tax and subsidy wash out, so it just equals whatever costs are at that new equilibrium emissions intensity. And basically, this just shows that you get the same outcome with any. If you make this a tradable performance standard instead, and you set the mu such that it would be the same as the equilibrium mu you would get with the tax. And same thing with an emissions cap. If the cap is set to meet the same emissions. You can implement it any way. So this is basically the output-based rebating version of, you know, that marginal abatement cost equals marginal benefit. You can implement that with a tax, or you can implement that with a quantity system. So if you don't have uncertainty and other things to worry about, any of these mechanisms will get you the same outcome. Okay, so just to summarize, okay, grandfathering versus output-based rebating. With grandfathering, you get a lump sum allocation. This equation here looks the same. Your decision to reduce intensity, because you're responding in the same way to the emissions price. You still have that emissions price there to signal reductions in emissions intensity, but what you're not getting is the price signal to reduce emissions by reducing output, because it's being offset now by the rebating allocation. Okay? In this case, with grandfathering, you have windfall profits. With output-based rebating, you have zero profits, but you have lower product prices, lower output prices, and thus higher equilibrium output. Okay. So do you think you have the same emission, if we just use this with an emissions tax, so we set the tax, do we get the same emissions with these two schemes? No. What do we get? Exactly, exactly. Because we've got the same emissions intensity, but we have more output, because we're subsidizing output. Or we're disincentivizing restricting output as a means for meeting the emissions target. Yeah? Because this is a transfer. They get this regardless of what they do. So they're going to produce, you know, and prices will be set according to all those marginal costs. And this doesn't show up on the margin. They just got it. They could shut down the plant and they get to keep it. They could produce twice as much. They don't get any more. So it doesn't affect production decisions. It's just a windfall, a transfer. It'll be the same. So you'll just have, in both cases, say you have like an upward sloping supply curve, in both cases you'll have some producer surplus. So then you can have some positive, you know, sector profits in equilibrium. But the effect of the subsidy is still going to be the same. You're still reducing your marginal cost. It's like shifting, it'll be shifting down that supply curve as opposed to shifting down a flat, constant marginal cost supply curve. I would say no, because because the subsidy is constant, that difference will be passed on in terms of the price. So you can think of it, okay, so this is the product market. So you have demand, and so these are production costs. So this is C as a function of Q, okay? If you lower your emissions intensity, this is going to drive up this. This is where it gets hard to do because you have two dimensions. Well, you need a third dimension. So say you've already made your choice of emissions intensity. This is your supply curve. So subsidy S will shift down the supply curve. Okay, so this would be the price and output with grandfathering, okay, and this would be your your profits. So then this, with output-based rebating, that's going to be the price, and this is the effective supply curve, and this is going to be your profits. So it's very, so you know, the only difference is going to be from this little area. But the effect, basically, the, you know, much of the incidence of the subsidy, it's going to depend on how flat or steep the demand curve, who gets the incidence of the subsidy. But that's similar with the, in terms of the emissions tax. So you can think of this as actually, so if that was my grandfathering, then it's plus mu. Okay, so there can be a little difference in terms of these areas, but the effect of the subsidy is, so if you think of this as the cost, the production cost without the tax, so the grandfathering system, where they don't get any rebate for that, will shift up the cost curve to be inclusive of the tax, and this is exclusive of it. So it depends on, you know, who bears the incidence. It'll be equivalent to who bears the incidence of the embodied carbon tax. So yeah, so it's a little different, but the intuition is still there, because in both cases, you know, marginal cost increases are going to be passed on. It's just starker in this model. Okay, so compared to lump sum allocation, we get less of an output price increase from regulations. We get less conservation. So that means for the same emissions price, we have more emissions. So then for the same emissions target, if we want to meet the same total emissions, what has to happen? I think it says it right there. Okay. Okay, so we're not doing it through conservation, so we're going to have to push harder on reducing our emissions intensity. And to signal that, that means the emissions price has to rise. So if we're thinking of, well, what happens in a cap and trade scheme where you have a fixed target and you move from grandfathering to output-based allocation, then you're subsidizing production. You're going to basically raise the carbon price. Because to meet the same target, you're going to have to do it some other way than conservation. And so this sort of reflects that there's going to be an efficiency cost to output-based rebating. You know, so you're going to have to have a higher emissions price to get the same emissions reduction. Okay, so you can kind of think of it like this. So this is the cost, the marginal cost with that you start out with. Now with the emissions price, you're going to improve your emissions intensity. That raises your cost a little bit. And normally that would decrease your output. With output-based allocation, then you get a subsidy. So you're not pricing the embodied emissions like you would. So the top line there is sort of what would happen with grandfathering, because you're pricing the embodied emissions and you have a bigger decrease in output. With output-based allocation, you don't price the additional emissions, but you have higher costs because you have to have a lower emissions intensity. So this is sort of the efficiency loss from using output-based allocation. Okay. Now it gets a little more complicated if you have rebating, but you also allow trading across multiple sectors. So the subsidy is going to depend sector by sector typically. You know, you're thinking about average emissions and production. So how it works can sort of depend on how the sector level cap or the standard is set. But one issue you have, so I mean, this was a big issue in you know, the benchmarking process, and also in the Waxman-Markey proposal, like figuring out what an appropriate emissions intensity is for each sector and what to base it on. And now the tricky thing is, though, if these sectors get to trade with each other, then partly what they can trade on is how well they can pass on additional costs to their consumers. So if you have sectors with more inelastic demand, so this is steeper, so more of this tax is going to be passed on to the consumers. You know, so they're not going to change, that sector isn't going to change its output decisions very much based on this. So you can shift more of the intensity reduction to sectors with more inelastic demand and away from the sectors that have more elastic demand. So you can, if you basically take the emissions rates, emissions intensities that would sort of in equilibrium have the same prices in each sector, but then let them trade, you'd think there wouldn't be any gains from trade because they have the same implicit emissions price. But if they have different opportunities for passing that along, you can actually create gains from trade. Let's see. Market power can be an issue here. So now, suppose you try to do this in a sector with only a few firms, okay? So they have some market power over in the product market, over the price, but then potentially also in the refunding market. So if you have if you have half the market share, then now you know half of what you pay into the scheme, you get back yourself. So that makes it cost less. And now this affects not only your production decision, because you're expecting the subsidy, but it also affects your emissions abatement decision. Your decision of emissions intensity, because now you know that if you reduce your tax payments, you're also reducing whatever your share of the refund is. Okay, so to the extent that there's market power, so that's the market share, little q over big Q, that diminishes your incentive to reduce emissions. So that's going to be an efficiency cost as well. And then you also see that, coming back in terms of your market share for the net emissions revenues. Of course, if in equilibrium that is zero, then that doesn't matter as much. The bigger concern is that you're changing the efficiency of the decision to reduce emissions intensity. So then to meet the same emissions target in a market, a very concentrated market, the emissions price is going to go way up because the price signal is being muted. Okay. There can also be issues if you have heterogeneous firms. So if all the firms are alike, then you can think, okay, well, I can actually design an optimal scheme here. Now, when you have imperfect competition in a market, you tend to have under provision of output because firms are maximizing, they're equating marginal cost with marginal revenue and not the price. So if they think they can influence the marginal revenue, they produce more, that lowers the equilibrium price that they can get. They have an incentive to withhold output from the market to keep the prices higher. They want higher prices. So were we all here at Mars seminar on Friday? Okay, so she was talking about market power there, where firms in these auction markets, they have an incentive to underbid. Some of the big firms have an incentive to underbid what they're going to provide because that pushes the price up. Okay? So now you have these two market failures going on. You have under provision of output, and you have your emissions externality. But if everyone is the same, everyone is symmetric, then you can actually design an optimal emissions tax system in this way, and the rebate now becomes helpful. So you can use the rebate, the subsidy, to counteract the under provision of output. So you're subsidizing output, trying to get these guys to produce a little more because that's more efficient. And then you could just correct for that by raising your emissions tax, depending on how many firms are in the market. On the other hand, though, if these firms are not all identical, then that's really tricky because you see from the, let me go back to this equation here. If the little qi's are all different, then we no longer have marginal abatement cost equalization. So little firms are going to be abating more, are going to be reducing their emissions intensity more than big firms. So in this case, if you have heterogeneous firms, then it's really, you can't reach an optimal allocation. You can do better with rebating in terms of dealing with the overall under provision, but you do get some shifting of output among the firms. In fact, output-based rebating then tends to shift more production to the high cost, to the smaller high-cost firms, and the larger firms, get a smaller net tax. On the other hand, what you could do instead, the way to get the optimum is not tie the subsidy to the emissions market. Have them pay the emissions tax and then give a fixed subsidy to output. And that does a better job without shifting among effort and making sure that those marginal abatement costs are equalized because the subsidy is not dependent on, the rebate isn't dependent on your emissions. Okay, so now it seems like there are a lot of reasons to think output-based rebating now is kind of a dumb idea. It's inefficient. It mutes the price signals to consumers to conserve or find substitutes. With less conservation then, it drives up carbon prices. And if you have a larger cap and trade scheme, that's also going to shift the burden around. So if you have rebating for some sectors, they're doing less, that means the carbon price is going to rise, other sectors are going to have to do more work. But on the other hand, there might actually be some reasons to think that output-based rebating can be less distorting. So one is, again, when we saw this case of inelastic demand, if the demand curve is fixed, then you're not going to have any change in output anyway. You're not going to use that as one of your means of reducing emissions, and so it doesn't matter. In general, when abatement is going to be done primarily through technological options rather than conservation. There may be behavioral failures in conservation markets. We hear about that a lot. So that might be another situation where you're less worried about the rebate. And it's definitely easier when products are identical and easy to define, so you know what output is. And so this is easy in electricity because it's it's a kilowatt hour. with other, some commodities, tons of steel, that's not too bad, although there are different qualities of steel, different grades. And then it starts getting really tricky, like when you start thinking, say, chemicals. There are lots of different chemicals, and they have very different values, and a ton is not necessarily a ton. The emissions associated with creating one can be very different from another. And so it starts to get really tricky, and the more you break it down into different subcategories. Aluminum, it depends if it's, is it recycled, or is it, made from virgin, or the emissions associated with that are very different. Do you want to differentiate among these? Do you want a bigger subsidy for making new aluminum than for recycling? You get into very tricky definitional questions, and then you can be creating different distortions among products that are really substitutes for each other. But on the other hand, there actually can be some situations where rebating can be efficiency enhancing. And so I think that's, we can't just have a knee-jerk reaction that this is a stupid policy. We might want to think about some situations in which it actually improves the efficiency of your policy system. So one situation could be when you can't get the emissions price you would want otherwise. There can be political feasibility constraints. Politicians don't want to raise prices on consumers, or they don't want to lose jobs in a sector. They want to maintain the competitiveness of that sector. And the other situation, so then, if it helps you get a higher emissions price closer to what the Pigouvian level would be, then that's a good thing. But there are even some situations where it reduces interactions with other market failures around. So if we're not in this, perfect world of first principles, then there may be some situations where we want it. And the ones that I have been focused on in my research are, and these are really I think the big motivators for often using these policies is, so the first one I'll call incomplete regulatory coverage. So we can think of that as the, the Kyoto Protocol, or the EU ETS, which is still, it's a little less lonely than it used to be, but it's still fairly lonely. There are a lot of countries that don't have emissions trading or emissions prices. So then you worry about leakage. So there are sectors that under the EU ETS, you have manufacturing sectors that have to compete internationally. And so if their costs go up, then what looks like it might be conservation by reducing their output, it's not really conservation if those emissions come back through imports. If consumers switch to imported steel, and that steel doesn't have to reduce its emissions intensity. So emissions leakage is one. Also, there's been a lot of literature in environmental economics on pre-existing tax distortions. In both labor and capital markets, so this is called tax interaction. And I can talk a little bit about that. And then imperfect competition, which we just talked about. So in the tax interaction literature, the problem is that, so when you have a tax on labor, say, you're putting a wedge between the supply and demand curves of labor. So you have, so anything then that further diminishes labor supply has an additional efficiency cost because you already have this wedge in there. Labor is already being undersupplied because it's taxed. And then what happens if you impose a carbon tax, that raises the price of carbon intensive goods in the economy, that lowers the real wage, which in theory, reduces labor supply, and then you get this efficiency cost. How big this is a dispute. But then, if this is something that you're worried about, then keeping those prices from rising as much can help reduce the interaction with that pre-existing tax distortion. Same thing with emissions leakage. Keeping those prices, those product prices from rising so much maintains more competitiveness, and you don't have as much substitution away to imports. Okay? But the trade-off is, thinking back, that you also don't have the signals to consumers to consume fewer energy emissions intensive products. So there's still an efficiency cost, but there can be a greater efficiency cost if emissions leakage is a problem. So for all of these things, and it's the same thing with imperfect competition, you have under provision of output. So anything that keeps the prices from rising further, gets you a little efficiency benefit. So I was going to do a break.